Welcome to Schrödinger's Chat, the podcast where I explore the real science behind the biggest questions in the universe, as well as some of the quirkier science we encounter every day. I'm Anna, a sixth form physics student with a lot of curiosity and a passion for understanding how the world works. From the smallest particles to the largest galaxies, join me as we unlock the mysteries and wonders of the universe and explore how physics shapes the world around us. What is infinity? Is it a number, an abstract concept, or is it just a theory? And how do we reach it? Or does it even exist anywhere in the universe? Well, if you haven't already worked it out, this episode we are exploring the mind-bending world of infinity, what it is, how it works, and how we can use it. We are looking at infinity and beyond. Infinity. What is it? What does it actually mean? Well, when you're a child, I think infinity feels like just a massive number. More importantly, it's a way to win any argument. Now, I don't know about you, but I have definitely had this experience as a child multiple times. Say you and a friend are arguing over something, perhaps who's better at something or who has more of something. If someone says, "I'm good at something," you can say, "You're better," and they might say they're the best. But we all know it's over once you say, "Well, I've got infinity skill," or whatever it is you're competing over. At this point, it can go one of two ways. Number one, your friend accepts that there's nothing greater than infinity. It's the maximum level or amount that anything can be, and you have won the argument. Or number two, your friend hits you with the infinity plus one move. Now, if this happens, then the game tends to progress into a second level. You start by adding more and more numbers to infinity, then it might be infinity times number or infinity times infinity. And once I definitely remember infinity to the power of infinity being used. But even then, I found any advancement you make can always be one-upped by adding 1 to whatever version of infinity you have reached. Now, what started as a childhood game has now turned into a bit of a mathematical dilemma. Infinity is infinite. But then how can you have infinity plus 1? And if you can add 1 to infinity, does this mean infinity plus 1 is larger than infinity, even though nothing is greater than infinity? Well, this is all part of what makes infinity so strange. The other thing that comes into play is that infinity isn't just about how high numbers can go. Of course, you can have infinitely negative numbers too, but also infinite numbers between two numbers. As in, between 0 and 1, for example, you could have endless decimals before you get to 1. Or in other words, you could divide 1 by larger and larger numbers to get numbers extremely close to 0, but never actually reach it. This starts to show that infinity isn't really a specific number or size, it's more of a concept. The variety in what infinity actually means was first revealed by German mathematician Georg Cantor. For centuries, infinity was just really big. You had one infinity and that was it. But in the late 1800s, Georg Cantor entered the scene. He basically said, what if there were different sizes of infinity? At first, I think that sounds really weird, and it kind of goes against what infinity feels like it should mean. Infinity is infinity, it's endless. How can you compare infinity to infinity? But Cantor showed you actually can. Take the whole numbers, 1, 2, 3, 4, 5, etc. They go on forever. You would never finish, but you could count every number in this set of integers. That's an infinite set. Then take the even numbers, 2, 4, 6, 8, and so on. Also infinite. Even though we've left out half of the numbers, which is quite weird when you think about it, as it makes you wonder whether you then have infinity divided by 2 or something. But the thing is, you can still assign a number to each one. 1 would go with 2, 2 with 4, 3 with 6, and so on. There are no leftover numbers. So both sets, integers and even integers, have the same size of infinity. Mathematicians call this a countable infinity. You can, in theory, list the members of the set one by one, even if you never reach the end of the list. So far, it's already pretty strange. But then Cantor took it up a notch. He asked, what about the real numbers, all the decimals, fractions, irrational numbers like pi or root 2? Can you line those up in a neat list too? Now this is where his famous diagonal argument comes in. Suppose you try to make a list of all possible real numbers between 0 and 1. Now this is quite hard to visualize just in your head by listening to this, so I highly recommend watching a video of it being done. But imagine you write them down like this. On the first line, you write 0.123456, etc. On the second line, 0.987654, etc. And the third line, maybe 0.33333, 0.3 recurring, and so on. You keep writing random decimal numbers between 0 and 1. Cantor then said that you could always construct a new number that's not on your list by changing the first digit of the first number, the second digit of the second number, the third digit of the third number, and so on. Then you would have a brand new number that wasn't on your supposedly complete list. That means no matter how hard you try, you can never list all the real numbers. They're not countable. They form a bigger infinity, an uncountable infinity. Now, at the time, this was revolutionary. Cantor had shown that infinity isn't one thing. It's almost like there are levels to it, with bigger and bigger infinities at higher levels. Cantor's discovery was actually so controversial that some of his fellow mathematicians at the time called it a disease. Even great mathematicians like Henri Poincaré dismissed it as nonsense. But over time, Cantor's work became the foundation of modern set theory and transformed mathematics. Mathematicians denote the smallest infinity, which is the size of the natural numbers, as Aleph null. The infinity of the reals is strictly larger, and we've just seen this by showing that natural numbers form a countable infinity, while real numbers form an uncountable infinity. Cantor discovered that there's no such thing as the infinity. Infinity itself has levels to it. And that's both amazing and mind-bending because it means that maths goes on forever and it gets bigger forever, not just in how high you can count, but between numbers. Now, if you thought Cantor's different sizes of infinity were wild, wait until you meet Gabriel's horn. This is one of those beautiful but slightly unsettling paradoxes. So picture this. You take the curve defined by the function y equals 1 over x for values of x that are greater than or equal to 1, and then you spin it around the x-axis. The result is a long trumpet-shaped object that stretches off to infinity. Mathematicians call it Gabriel's horn, named after the archangel Gabriel, who, in tradition, blows a horn that echoes through eternity. Very fitting name if you ask me. But it gets really weird when you calculate its properties. For the volume inside the horn, if you do the integral, it turns out the horn actually encloses a finite amount of space. Specifically, it converges to pi cubic units. That means you could fill the entire infinitely long trumpet with a finite bucket of paint. Pi cubic units of paint, if you like. But if you try to calculate the surface area of the horn, it gets really weird. When you try to find out how much paint you'd need to cover the outside of the horn, the integral diverges. The surface area is infinite. So that's your paradox. You can fill Gabriel's horn completely with a finite amount of paint, but you would never have enough paint to cover its surface. This seems impossible. How can you fill something without being able to coat its outside walls? But that's the strangeness and power of infinity. It completely destroys our intuition and makes us question our assumptions and mathematical reasoning. For me, Gabriel's horn is a really good reminder that infinity isn't just about big numbers. It's about how it can change geometry and our analysis. It forces you to confront the limits of what's real physically and what we can get away with in abstract maths. After all, no actual trumpet could stretch infinitely, but the idea shows us where maths can go when it's freed from the constraints of the real world. And remember, the maths actually does work. It's not impossible to calculate this result. Let's look at some more paradoxes of infinity, because I think they're a really great way to demonstrate the sheer range of meaning and layers to infinity. Let's go back 2,500 years to ancient Greece, where a philosopher called Zeno of Elea posed one of the most famous paradoxes, the Achilles and the tortoise paradox. Here's the basis of this paradox. Achilles, the fastest runner in the world, races a tortoise. But to make it fair, Achilles lets the tortoise start ahead of him. Now, Zeno argues that Achilles can never actually catch up, because every time Achilles reaches the spot where the tortoise was, the tortoise has moved a little further ahead, and by the time Achilles reaches that new spot, the tortoise again has moved forward a little bit more. This continues forever. There are infinitely many points Achilles must reach, and so Zeno says Achilles will never actually overtake the tortoise. Now, obviously, in the real world, Achilles would go straight past as soon as the race started. But Zeno's paradox shows that tension between infinite processes and physical motion. Another way to apply Zeno's paradox, which I prefer, is if you consider crossing a finite distance. Think about clapping your hands. Your hands start a fixed finite distance apart. Say they start 40 centimeters apart, and you only move one hand to meet the other, keeping one fixed in its original position. Now, one way to consider the journey of one of your hands to meet the other is to think about the distance halving and halving again until you reach the other hand. So you halve the starting distance, so your hands are now 20 centimeters apart, then again to 10 centimeters apart, and again to 5 centimeters. And in theory, you could keep halving the distance, your hands getting closer and closer, but never quite reaching each other. This would suggest that there's an infinite distance between your hands. Now, obviously in real life, this can't be the case. It's definitely completely possible to close the distance between your two hands and clap. But it makes us think about what infinity means when we're not just considering it on a static number line, but when it's in relation to motion and change over time. Now, this is essentially calculus, but back then no one had calculus, so infinity was still this mysterious, untamed thing. Today, with limits and series, we know an infinite sum can converge to a finite value. For example, a half plus a quarter plus an eighth adds up to 1. So Achilles could pass a tortoise, but Zeno wasn't wrong to highlight the weirdness of infinity, and he basically foreshadowed the invention of calculus by centuries. Let's fast forward to the 20th century, and mathematician David Hilbert gave us one of the most famous and mind-bending thought experiments in infinity, Hilbert's Hotel. Imagine a hotel with infinitely many rooms, all occupied. You'd think it's full, right? No available rooms. But in an infinite hotel, that's not a problem. If a new guest shows up, the manager can simply ask every guest to move to the room with the next number. So the guest in room 1 moves to room 2 moves to room 3, and so on. Room 1 is now free. And there you go, the new guest has a bed. Now suppose an infinite bus of infinitely many guests arrives. Surely this creates an issue for the hotel. But actually, it's no problem. Ask each guest to move to the room that's double their current number. So the guest in room 1 moves to room 2, the guest in room 2 moves to room 4, and so on. That leaves all the odd-numbered rooms free, which is an infinity of space for the new arrivals. So everybody on the infinite bus can find a room in the infinity hotel. Now this comes back to that childhood one-upping situation I talked about earlier on in this episode. Adding things to infinity still gives you infinity. Infinity plus infinity is also infinity. But Hilbert's Hotel is so important because it makes those super abstract ideas more concrete in a way that feels both funny but also kind of unsettling, because it feels like you're breaking the rules. It highlights that infinity doesn't actually follow the normal arithmetic rules that we expect from everyday numbers. In fact, when you solve the hotel issue by just adding 1 or doubling the number on the rooms, it kind of feels like cheating. But that's the point. With infinity, you can do these weird counterintuitive things. Now, so far, we've been looking at infinity in the realm of maths. Hilbert's hotel, Zeno's tortoise, Cantor's uncountable sets. But what about infinity in physics? Well, physics doesn't always go nicely with infinity. In fact, it can cause physicists a lot of issues. Take cosmology. The big questions are, is the universe infinite? Could there be infinitely many parallel universes? On one hand, space could just keep going on forever. Infinite galaxies, stars, infinite planets. That would mean that somewhere out there, every possible configuration exists. A planet identical to Earth, another version of you, another version of me, somebody recording this same podcast, but maybe in that universe I have a slightly different accent. But we don't know. Some theories suggest the universe is finite, but unbounded, like the surface of a sphere, only in a higher dimension. You could travel forever without hitting a wall, but it's not actually infinite. This is exactly like a sphere. You could go round and round the surface of a sphere, but you would never hit an edge or a corner or a wall. But of course, we know that a sphere is not an infinite shape. Then there's the infinitely small. In quantum mechanics, particles sometimes look like they have no size at all. But try plugging that into equations and suddenly you get really nonsensical values and infinity spitting out everywhere. In fact, early versions of quantum field theory were plagued by this problem, so much that physicists had to come up with what's called renormalization. This is basically a mathsy trick to sweep the infinities under the rug. Richard Feynman once said it felt like hocus pocus, but hey, it works, and it gave us the standard model of particle physics. This is the theory that classifies all known elementary particles and describes 3 of the 4 known fundamental forces: electromagnetic, weak and strong interactions, with the 4th force not described by this being gravity. And then, perhaps most mind-bendingly of all, there's black holes. At the very centre, in what's called a singularity, the equations of general relativity predict infinite density and infinite curvature of space-time. Most physicists take this to mean our current theories break down at that scale. It's not that the universe literally contains infinity in a physical sense, but rather that infinity is a sign that we need to develop new physics to allow us to understand it. So infinity in physics is kind of a paradox in itself. On the one hand, it inspires these epic ideas about endless universes and infinite possibilities. But on the other hand, it's also a troublemaker, breaking equations and forcing scientists to rethink their theories. But ultimately, I think it's a good thing. It forces physicists to question our current understanding of physics and seek new physics to explain the unexplainable. Infinity is at the edge of physics, but maybe one of the most important things for understanding the true nature of the universe, and I think that's really exciting. Now, infinity is cool, but this episode is finite, so that's all I have for you today. I really hope you have enjoyed this episode. If you have, please go and leave a review or a comment and recommend it to your friends. If you want more Schrödinger's chat related content, go and check out the Instagram account. You can find me at Schrödinger's Chat Podcast on Instagram. Here I post all sorts of content, from extra bits relating to the episodes, science book recommendations, and just general nerdy science stuff. So if you enjoy this podcast, I think you'll definitely like some of that stuff. So do go and have a look. As always, thank you so much for listening. I really appreciate it, and I'll see you in the next episode. But until then, stay curious and don't go racing any tortoises. You might never win. Bye!